This is the second half of the kernel memory allocator discussion, and you'll remember that last time we talked about a number of allocators using more traditional techniques that you would see in a user space allocator, maybe in one that you wrote for a CS24 class near you. We had resource map or sort of explicit free list allocators, power of two free list allocators, also known as segregated fits or segregated free list, McCusick-Carroll's allocator, which is the allocator that was used in certain versions of BSD, and binary buddy allocators, which are very neat, and they're used in Linux, actually, for the page management. We'll talk a little bit about that today. The allocators, I say, are refinements, but I think that may not be precisely true. They're just sort of a progression of ideas that are all related, and so you can see the theme through them. But they all have their strengths and their weaknesses. As we went through last time, I talked about the benefits and the drawbacks of each one, and why ones are appealing in some circumstances and not in others, and some of the limitations and difficulties you run in with them. The buddy allocators are fast, and as I say on the slide, they're nearly as fast as the McCusick-Carroll's allocator. The McCusick-Carroll's allocator, remember, takes whole virtual pages and chops them into power of two size chunks based on a request, and it tends to be pretty easy to do that. I actually would think that allocating a certain size memory chunk might be faster on a binary allocator because it tends to have really simple free list management. Let me see if I can trying to figure out how to make the participant ding sound distracts me, so I'm going to turn it off so that I don't get what's that? So but anyway, yeah, so these allocators, because they maintain free lists, make allocation very fast. And so I think where buddy allocation is slower than McCusick-Carroll's is the coalescing of blocks with their buddies, as we talked about last time. So internal fragmentation is always a challenge, because if you're handing out power of two size memory chunks and somebody needs 24 bytes, they need 56 bytes, they need not exactly power of two size chunks, then your allocator is throwing away a lot of space to internal fragmentation, and that can be really problematic. And so we're going to talk more about ways of avoiding that today, and the ways that we have to avoid this are pretty awesome, and I love them. So we also haven't really considered virtual memory. The McCusick-Carroll's allocator definitely takes virtual memory into account. Buddy allocators, you can say, are agnostic to the size of a virtual memory page, but they don't really take it into account in the same way that we'd like to in our operating system kernel allocator. Okay, so we have this virtual memory system, and I'm really curious how well everybody understands the virtual memory system, because I don't know how strongly you focus on that in CS24. But the computer has a certain amount of physical memory. You could think of it as being 2 gigs of RAM. You could think of it as being 8 gigs of RAM. Anybody who builds a computer or buys a laptop and it says, this computer, like my computer, has 32 gigs of RAM. Well, that's physical memory. And the processor presents this abstraction of an isolated address space for every process. And the process may have a much larger address space, i.e. it can access more bytes than physically exist on the computer. So on 32-bit, like IA32, you'd have a 4 gigabyte address space. Now, what happens if you're running 100 processes? Does that mean your computer needs 400 gigabytes? No, it just means that each process has a 4 gigabyte address space, and the operating system can figure out how it wants to map the available physical memory into the address space of the processes that are ready to run or are running. It's even more complicated with 64-bit. So probably all of you are using x86 64 computers, unless you happen to be watching this on a phone or something like that. And x86 64 has a 48 48-bit address space, which you might say, why doesn't it have a 64-bit address space? We're not there yet. And so 48-bit address space is huge and almost guaranteed that you do not have a computer or access to a computer with the same amount of physical memory as you can even map into a single process's address space. So you have physical pages, or physical page frames, we usually call them, and you map those physical frames into the virtual address space, and now the program can actually use that chunk of memory. So this is cool, and it's very powerful of a technique, but because we have this mapping of virtual to physical, virtual pages to physical frames, the process doesn't really care what order the page frames appear. Like, is this virtual page 1 physical page 93? Is virtual page 2 physical page 316? It doesn't care if the physical pages are in order because it only sees the virtual address space. Programs can only ever emit virtual address spaces. Even the kernel uses virtual addresses when it runs. So we'll talk a lot about that when we get into the next project. So I have on the slide here, kernel allocators sometimes care about whether the physical page frames are contiguous. Page frame 1, page frame 2, page frame 3, so forth. Okay, there's basically two situations where we care about this, and only one of them is really that severe. Otherwise, we just kind of don't care. User space programs don't care one tiny bit what order the physical frames are, because you have this mapping table from virtual address to physical address, and the virtual addresses are what the program emits. So it gives not one care what order the physical frames are in. Doesn't affect hardware caching, doesn't affect the virtual memory system, so the program doesn't care. Now, there's two reasons why the kernel itself does care, because one of them is that managing and changing the virtual to physical address mapping does incur costs. And I mentioned before the translation look-aside buffers. This is the fastest hardware cache on your entire processor, because when you have to look up the mapping from a virtual page number to a physical page number, and that's stored in memory, then you're incurring an extra 1 to 400 clocks per memory access. And nobody wants that. So we load those address mappings into this translation look-aside buffer, and that cache can become invalidated when we change the mapping. And so because of that, we have to do a TLB flush, it's called. And that means that some of our memory accesses are slow after that. And so the kernel would like to avoid this, since everybody benefits or suffers when the kernel is fast or slow. The kernel tries to set up its memory mapping so that it has to touch the translation look-aside buffers as little as possible. And so one of the ways that it does that is just by consuming a range of physically contiguous page frames right at the beginning so that it doesn't have to alter the address space mapping afterward. Now, I mentioned here that this is not super critical. In fact, most of the time, this is actually not going to be a big deal. The takeaway is not that they have to be physically contiguous. The takeaway is that we want to change the address mapping of the kernel as little as possible. But the place where it really matters is when it comes to peripherals that are smart enough to talk to memory directly. So I have this picture on the slide, and you can see that there's a number of things going on. This is where your program runs in the CPU, and that's also where the memory management unit is. That's the thing that does virtual to physical address translation. So what comes out on the bus is physical memory addresses, and they hit the I/O bridge, and based on control signals from the CPU, it'll either access main memory or it'll access a peripheral bus. Like this might be your PCI bus. And so the CPU, the kernel, can set up an interaction, or it can talk directly to a peripheral on this bus using the I/O bridge, but then it can let the peripheral do some things on its own, so the CPU can do calculations in the meantime. So this is the really cool thing. We call it direct memory access. So the CPU sets up a DMA transfer. You can see here we're going from the CPU to the disk. So we're setting up a disk read. We're saying, hey, we want to read 10 sectors starting at this sector number, and this is where I want you to store it. And so then the peripheral, waits. So how many ever hundreds of thousands or millions of clocks for the data to show up on the device so that it can be loaded into the disk controller. And then the disk controller needs to move that into main memory. We would love for this to not involve the CPU at all. We'd love for the CPU to be able to do other things so that our computer can be more efficient. We'd like to overlap these operations. Okay. Once that operation is finished, the peripheral can signal to the CPU that the operation is complete by raising a hardware interrupt. And so there will be a specific interrupt handler on the OS kernel for the disk controller, and that thing will be notified, and then it can query the disk controller to find out what was finished. And it'll know, this is the thing that I set up for it to do, and it will know that the data is now available in memory or it has been written to the peripheral. Okay? So very powerful, useful technique. Now here's the key question I have on the slide. Does the peripheral use virtual addresses for interacting with memory, or does it use physical addresses? This is the question that you have to think about, because look where the memory management unit is. We've got this thing right here on the CPU on the other side of the I/O bridge. The addresses that the disk controller is reading and writing are physical addresses, except in one special case. So since these peripherals use physical addresses to interact with memory, they have different constraints on what memory addresses, memory ranges they can write to than the CPU does, than the kernel does, than the programs do. And so the kernel needs to take this into account to make sure that it configures memory utilization in a manner that works well for the peripherals. So that's the big reason, and this is the most important reason why sometimes we need to have physically contiguous sequences of page frames allocated by the kernel. Okay, so peripherals often use these physical addresses. You can read some about this in the Linux kernel archives. There's lots of interesting articles about this kind of thing in the archives. So if you have a DMA transfer, direct memory addressing transfer set up, and it needs to write to multiple pages in sequence, then those need to be physically contiguous pages, because that's the address, that's the kind of address you're giving to the peripheral anyway. Okay. Also, you'll notice I say it frequently has to be within a specific range. So the peripheral may only know how to write to a certain subset of the address space because it's a peripheral. It's been hardwired and so forth to be able to do certain things on the bus. It's not as flexible or powerful as the CPU running software. Okay, so for DMA support, kernel allocators often have to have a way of allocating physically contiguous pages. Now, Pintos doesn't care because Pintos is simple, and Pintos uses really old-fashioned, old-school interactions with the emulated hardware, and specifically, it doesn't really have a notion of DMA transfers. It does things in a very primitive and simplistic manner. So this is fortunately not something you have to worry about. But if you're wondering why the boundary between user space and kernel space is called phys_base, it's because that is the start of the physical page mapping in kernel space. So it's called phys_base because it's the start of the mapping of physical memory into the kernel's virtual address space. We'll get into that a lot more in a couple of lectures. Okay, the other thing that I want to mention about this, just as a point of note, some peripherals are smart enough to know about virtual addressing. They have this special thing called an IOMMU. So it's a memory management unit, but it's on a peripheral. And so the IOMMU support allows some of these peripherals to be much more sophisticated and much less sensitive to having a range of physically contiguous page frames to write into. So, technology marches forward as always. Okay, the way that we tend to do memory management and memory allocations inside the kernel these days is using what is often called cached object allocators or pooled object allocators or sometimes object pool allocators. Basically, we recognize that there are kind of a limited number of types used by the kernel. You got your process control block. You've got your file struct, keeping track of the file details of an open file. You've got synchronization primitives and the structures for those. You've got small buffers that you might use for the keyboard or other devices. So you tend to not have a huge number of arbitrarily sized types that you manage inside of a kernel. And because of that, we can just say, we're going to set aside this giant chunk of memory for this kind of object. And any allocation of that kind of object comes from a specific region of memory. And what this means is we basically get rid of both internal fragmentation and external fragmentation. Internal fragmentation goes away because we need very little bookkeeping, because the kernel knows this kind of object comes from this place. And we get rid of external fragmentation because all the allocations in a certain chunk are exactly the same size. So it's easy to do allocate, free, reallocate. You just keep reusing these same chunks. It's the same size as you needed before. So it just eliminates a whole class of problems that emerge from trying to implement general purpose allocation. And I'll mention, this is a great technique to use in user space as well. If you ever have a program that has to manage a large number of objects that are all the same type, all the same size, maybe with different lifespans. And a great example of that is a particle simulator. Particle simulators oftentimes use cached object allocators to make it really fast and simple to manage all of the data structures for particles. Okay, so most allocations and releases will be constant time. The vast majority will be constant time. Every once in a while, you need to go to the allocator and say, hey, can you get me another chunk of memory to use for this kind of object? That takes more time because it may involve paging out memory, things like that, and that obviously takes some time. And then, of course, you have to periodically go collect garbage or clean up regions of memory that are no longer in use. If you have varying time varying memory requirements, then you want to reclaim the stuff that's no longer really being used. Okay, another benefit of these cached object allocators: improve CPU cache usage. Yay! This is another one of those things that I don't know how much is discussed in CS24 any longer, but the hardware caches on the processor are extremely important for creating maximally performant programs. Like, it is so useful to know how they work and what they do so that you can make programs that are fast. Now, the problem is the word cache is going to appear on these slides and mean two different things. You've got the cached object allocator, which just maintains an object pool, and that's the cache in that context. And then you have the CPU hardware caches, which is a different kind of cache and it's built into the processor, and you'd like to play nice with it so that your program is super fast. So basically, when you have memory blocks that you're returning that are always aligned on powers of 2 or multiples of powers of 2, then that doesn't play very well with some of the most common hardware cache architectures. I mentioned direct map caches, and I mentioned set associative caches. These hardware caches have to be as fast as possible. And one of the techniques they use is to try to place cache data in specific locations based on the address being accessed. Well, if all your addresses are multiples of powers of 2, then you're going to start getting specific cache blocks targeted within the hardware caches. And that's going to make the cache appear to be smaller than it actually is. And that will reduce the performance of your programs. So that's a challenge with these power of 2 free list allocators. if we take a huge chunk of memory that's contiguous and we chop it up into a whole bunch of objects of the same type, unless that object is a power of 2 in size, which usually it's not, it'll be some multiple of 4, multiple of 16 perhaps, but it's not going to be one of the larger powers of 2 where it really starts to have a negative impact on hardware cache performance. When you chop that big chunk of memory up into these smaller bits, the addresses are going to be much more uniformly distributed and will therefore play much nicer with the hardware caches. So this is a hugely important component of the benefit of these cached object allocators. They play a lot nicer with the hardware caches on the processor than power of 2 allocators do. Okay, I hope that makes sense. If you have any questions about that, feel free to ask later. Hardware caches are really cool and confusingly sophisticated, as well as simple at the same time. So how to play nice with them is really important if you need to write super high performance software. Okay, so let's talk about the Mach allocator. So this is the Mach operating system developed by CMU, and it has informed the design of several different OSs, and in fact is directly influential on Mac OS, which is taken the Mach kernel and customized it in various ways and built around it. So Mach has this thing called a zone allocator. And this zone allocator has a different zone for each type of thing that you might allocate. So each type of thing will be its own size. And there's also a garbage collector that goes through and cleans up, reclaims unused pages at an appropriate point in the lifetime of a virtual page. Okay, so the zones are just regions of memory divided by type of object. So each zone actually has a string name, and you can actually query the zone allocator and say, hey, what kinds of objects are you allocating? What sizes are they? How many do you have in flight? How many are available? Blah, blah, blah. You can ask it all these kinds of questions. So the zone has these kinds of, oh, I'm sorry, I'm getting ahead of myself. Yeah, so these are the kinds of things that go into different zones: process and thread control blocks, virtual memory map objects, semaphores, pipes, kernel notification objects, and so forth. Zones, being managed by the kernel, are also in a zone. So you have a zone of zones that's used to allocate and manage the zone objects themselves. So you can see how this zone allocator is a nice generalized thing. Oh, and yeah, so I need to update this to just say Mac OS because Apple no longer calls it Mac OS X. They now just call it Mac OS. But if you happen to have a Mac and you happen to be bored right now, you can always type sudo zprint and you'll get a dump of all the zones that are currently in use by the Mac OS Mach zone allocator. So it's kind of fun to poke around and see a little bit of how that's used. And you'll notice all kinds of things in there, like some of the memory is wired and some of the memory is this and some of the memory is that. And you can read about Mac internals to see what all of those things mean. Okay, each zone is a cache of objects of a specific type. So this is what I was saying before. Here's the zone struct, or at least a good chunk of it. And you'll notice here that zones have names. The name is just sort of a string representation of the type. So you might have semaphores, threads, and you'll even see things like buff16, buff64 if you want to get a 64-byte buffer or something like that. And so we have the name of the zone, the size of the elements. So that would be elem size here. Notice there's a number of VM size T's here. So elem size is the element size. And then you have the sizes of the zone. Current size of the zone, the maximum size of the zone, how much to grow it by when you need to grow it. And those are all related to the virtual memory page size, because we always only grow or shrink by the virtual page size. And then also how many elements, how many objects are in use. You'll see free elements is also there, and there's a few other details as well. Okay, The zone has a linked list of available elements. And so in this way, it's similar to an explicit free list allocator, except that you know that all the chunks in that free list are exactly the same size. They're exactly the size needed for that object type. So the free elements thing, oh yeah, VM offset T, I forgot about this. This thing is a pointer to the first available element. So that means that if there are elements available, allocation is a constant time operation. We like constant time allocations. There are also virtual pages associated with the objects in the zone. That should make sense. This is where they're actually stored. So let's say that we have a situation where a zone has a certain object type, but we need to grow the number of objects in the zone. So you can see here, the available memory must be increased, so we request a contiguous region of virtual pages. So this is virtually contiguous. This is in the kernel's address space. The kernel has to manage its memory, just like it has to manage the the virtual address space of user processes. And so here we have 3 virtual pages that are being devoted to more objects of that zone's type. So normally this will be what is stored in Lec16, but if we have a situation where memory availability is very low, then it'll just be the minimum size necessary rounded up to a whole number of virtual pages. So this Alex size is a preferred suggested value, but it's not the requirement if it can't be met. Okay, the next thing that we do is we take this chunk of memory that we now have and we chop it up into elements of the specified element size. Now, what do we mean by chop it up? Well, it's just sort of like we impose some structure on this sea of bytes. So you can see that whatever the element size is here, I chose an element size and we hit the end of the page and it wraps around to the next page. That's fine, we don't mind. We come down here, we wrap around a little bit again, and then we have a little bit of excess space. So this is internal fragmentation, but is very small because generally we get many more objects for the section of virtual memory pages than we have waste at the end. So generally this is going to pay off handily in the long run. Okay. The elements are linked together into the free list. So you can imagine the zone allocator, when it gets a new chunk of memory, it knows element size, and it just goes through and plops down free list pointers to link all these things into a chain, and then it makes sure to incorporate those into free elements. So maybe this pointer at the end would go to any available, previous free elements. It could still point to that, or maybe it'll be null to indicate that there are no more free elements. And the free elements pointer will point to the first element in this free list. So now we're ready to go. If somebody has a request, we can just pull off an object off of the pool and hand it to them and update our free elements pointer. So that allocation effort will be constant time. Okay. So there you go. That's pretty easy. Are there any questions so far? I mean, hopefully this is like, yeah, that looks really obvious. Okay. So when someone needs an object of a particular type, they call this thing called zalloc. And this is a kernel operation. And you'll notice here that you have a zone T, so that'll be a pointer to this zone. So this thing is the zone. And normally you don't want to look that up because if they're maintained as a linked list, you've got to walk through the linked list to find the zone. So if you know you're going to use a certain kind of zone all the time, you just cache a pointer to the zone, and then you can call zalloc without having to look up the zone each time. If the zone has no free elements, then the zone memory will be increased. So that is just what I was saying before. And then the zone allocator will just pull the first element off the free elements and then update the pointer to the next free element. Easy peasy. Can you clarify the difference between this procedure and the allocation of the cached object allocator? I'm not entirely sure I understand the question. There are 2 kinds of allocations that occur. This allocation request comes from other parts of the kernel because they need to have a struct of a certain type to maintain some kernel information, some information pertinent to the kernel's operation. The allocation that I just described is setting up the pool of available objects as opposed to asking for one of those things to actually use. Does that help clarify? Did I understand the question correctly?
Uh, I just because in the other one it was also like contiguous like pages of memory, and then everything that you were allocating was going to be the same size in
Mm-hmm.
the cached object allocator, and it seems like this is similar.
Oh, this is the
Um,
same thing. Yeah, we're
yeah.
still talking about it. Yeah.
Oh, is this like a subset of the cached object allocator? Because I thought the cached object allocator also had like a larger contiguous memory block, and then everything was assumed to be like the same size, like the same
Um,
like.
the mock zone allocator is an example of a cached object allocator.
Oh, okay, yeah, that makes sense. Okay, thank you.
Yeah, no problem. Yeah, so today all we're really going to talk about is actually two kinds of cached object allocators. We're going to talk about, and it depends on whether or not I actually get to the second one. But the mock zone allocator is a really prominent example of a cached object allocator. And so that's what I'm showing you here. This is a pool of objects available for use. And then the other one we'll be talking about is the Linux slab allocator, which is it's got three different things. It's got slabs, slobs, and slubs, and but they're all also variants of this cached object allocation mechanism. So hopefully that clarifies what we're talking about here for everyone. Cool. All right. Now, there is a garbage collection mechanism that's built into this zone allocator, because you can imagine, let's say I'm doing process control blocks or thread structs, or I'm doing file structs because I need, processes open files, close files, so we allocate and then release file objects and so forth. So you can imagine that we have all these available objects in a zone, and then somebody asks for them, we hand them out. This free list starts to go away because we're using them, and then we also free the objects eventually. So then we have to figure out what goes on with this thing. So there's a special mechanism in the mock zone allocator, basically called a zone page table entry for each of these pages that are part of a zone. Okay. And you'll notice they have a few details, a few basic details: alloc count, collect count, and next. And so at initialization, the alloc counts are all initialized to how many objects have some presence in that page. Okay. And you'll notice when I say have some presence in that page, so the last object on the first page is in the first page, so its allocation, it's represented in the alloc count. The fact that it also has some space in the second page means it's also represented in the second page's alloc count. So we just keep track of what pages each object falls into with the alloc count. And you can imagine the alloc count can easily be initialized as part of setting up this memory chunk in the zone. It's pretty easy. Okay. So the garbage collector goes through and sets all the collect counts to be 0. Then what the garbage collector does is it follows this free elements list. And basically, it looks for the virtual page or pages that the element falls within, and then it increments that page's collect count by 1. Hopefully you can see where this is going. If I have this situation here and I say, oh, this object is in this page, this object is in this page, this object is in this page, blah, 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 then the collect count would be 6. I come over here and 1, 2, 3, 4, 5, 6. I have a collect count of 6 again. So if the alloc count and the collect count are the same, we know there are no in-use objects in that virtual page. And that means that we can free that virtual page. Hopefully everybody sees that. Okay. So yeah, so once the garbage collector has gone through and chased down all the free element lists, then the garbage collector can make a second pass and look through all these, I can't remember what they're called. I'm going to go back a slide because I want to remember what they're called. Make sure I call these zone page table entries. So it chases through all the zone page table entries because they're also linked together in a list. And if it sees a page table entry with alloc count and collect count being the same, it says, okay, I can reclaim this page. So it queues it up. It says, this is available for use if we need to. So that's the idea there. Now, don't forget, of course, that if you reclaim a zone page table entry, you need to remove those objects from the free list. Otherwise, you're going to end up in la-la land when you try to follow the free elements pointer. So that's one of the challenges that you have with the garbage collector, but at least you can tell when you can get a virtual page back. So that's an encouraging, a beneficial thing about this approach. Okay, the pager is basically the thing that has to figure out what page frame needs to be evicted so that we can use it for something else. So when that pager is invoked, that's when this garbage collection mechanism would run. And particularly in low memory conditions where the system needs to be more aggressive about trying to identify and reclaim memory, it would be run in those situations. Okay. All right. So there are also allocations for buffers. I mentioned this before, and you'll see that if you enumerate with that sudo zprint command on a Mac, you'll see that there are buffers of various sizes that you can request. And so there are specific zones for those kinds of allocations as well. And so this is how this is able to be a nice general purpose allocation mechanism for the kernel. Okay. That is that. Zone allocator is great as long as you're not invoking the garbage collector. That's where it really starts to slow down. As I mentioned here on the slide, allocating memory, asking for an object from a pool, super fast, releasing an object back to a pool, super fast. All of these things are really nice. The difficult part is just the garbage collector because that may impose a latency on some other operation. And so that's where the real dangers of these kinds of mechanisms show up, is when you are in the middle of doing something fast and unexpectedly the garbage collector gets triggered. That's why, games programmers don't like using languages with managed memory, because they don't want to be affected by a garbage collector kicking off when it's unexpected. So that's really the primary issue that anyone has identified with the zone allocator. Like I say on the bottom of the slide, though, you can't imagine that the problems are that bad because Mac OS has been using it forever by now. So it was introduced with Mac OS X and continues to be used to this day. So it can't be that bad of a problem. Anyway, so that's the zone allocator, a good example of an object pool allocator. I think it really well illustrates the approach, the principle that is at work here. And if you ever have the opportunity, I hope you get to play with a object pool allocator, because they really make allocation fast. I tell you what, they're kind of fun. I used to have a CS124 exam problem built around building an object pool allocator. They're just really neat little approaches. Okay, the other main pooled object allocator that you'll see in kernels is called a slab allocator, and it's basically identical to zone allocators, except the data structures are just arranged differently and managed differently. That's really all there is to it. So a slab is a run of virtual memory pages that are contiguous, of course. And you can also tell the slab allocator, I need this slab to be physically contiguous if you happen to be setting it up for buffers for the disk controller, or buffers for the network controller, or buffers for sound devices and so forth, if those devices need to do DMA transfers in physically contiguous address ranges. Then you have a cache, which is objects of a specific type. And you'll notice that I say on the slide that a cache is equivalent to a mock zone. So a cache is for a specific type of object, and it will contain some number of slabs for that type. Okay. And of course, the cache could also have 0 slabs if no objects of that type have been in use for a while. Okay. So an object, these slabs are chopped up into little chunks that are exactly the size of the object that they're for storing. And so it's certainly possible, as before, that an object may span the boundaries of a virtual page. This is fine. We don't mind because it's still virtually contiguous and the software won't know any difference. Okay, let me see what's going on here. All right, so here's a picture of what a slab might look like internally. And this is one mechanism for structuring a slab. There's actually 2 primary mechanisms used. So we have pointers to other slabs in the same cache. So pointer to a list of other slabs in the cache. We have things like that, previous, next slab. Pointer to the first object in the slab. So you can see that up here we have a pointer to the start of the free list, if you will. So we maintain a free list in slabs. And so the slab header will say this is where the first free object is, and then each object will point to the next object. And then a lot of times you also have these descriptors, which sort of have more information about these things. Okay. And yeah, like I say on the slide, if the object is free, the descriptor will say, here is the index of the next free object. So yeah, actually, I guess I misstated this slightly because the other approach is in a subsequent slide. In this layout, the descriptors are used to chain together available objects in the slab. Okay, so we don't actually link the objects themselves together. We link them through the table of descriptors. Okay. Now you'll notice that this header part consumes some space in the slab. And this is kind of the big benefit of the zone allocator, is the zone allocator factors that information out into a separate location, which of course is allocated in its own zone. So slab allocator is a little bit less efficient in how it manages the memory, but it's also the header information is right there. And so I suppose you would get some hardware caching benefits from laying it out this way. Okay. So as I say on the slide, you may actually factor out this descriptor information into a separate object. It really depends on the size of the objects that are being stored in the slab. In particular, if objects get above a certain size, then the descriptors are factored out because we want to try to pack as many of these objects into the slab as possible, and the descriptors eat up some of that space. Okay. So we have this descriptor separated out, and you can see the slab itself is going to be just fully packed with objects. Okay. Let's see what else we have here. Small objects, it will actually do it more like the zone allocator, where the individual objects are linked together into a linked list. Okay. So you can see how there's variations. Slab allocators will use various approaches depending on the size of the object being managed. That's also where slab, slob, and slub come from in Linux, because they're just different mechanisms for managing the information in a slab for the kernel allocator. Okay, slab allocators, they frequently include caches for general kernel memory allocations. So I need a 32-byte buffer, then the slab allocator will have a cache for little buffers of that size, and so it'll have slabs devoted to that if necessary. And as I was saying before, the slab allocator supports the ability to say these pages need to be physically contiguous, or these pages do not have to be physically contiguous, just in case the slab happens to be for hardware DMA buffer support. So it can manage that. And it tends to be that the kernel will set aside a significant chunk of physical memory page frames at bootstrap, because the physically contiguous page frames will also become fragmented over time as you have allocations and deallocations and reallocations and so forth. So since that's difficult to deal with, the easiest thing the kernel can do is just grab them all up at first when nobody's run yet, and then put those into its own pool that it can use for DMA friendly buffer requests. So that tends to be how kernels will handle that particular problem. So this is how the Linux slab allocator works. So it's got DMA friendly and also non-DMA friendly buffers, so that it can have stuff for hardware specifically or for software that doesn't care. And there's one other thing I wanted to mention about slabs, which is kind of cool. But the other thing that I wanted to say about this, what was the other thing I wanted to say about this? Oh yeah, I don't mention it in this slide yet, but I think I might mention it at the very end. Linux uses a two-level mechanism. It uses a binary buddy allocator to manage the virtual pages and physical page frames. And so this is nice because you remember that the big benefit of the buddy allocator is that when you have two buddy blocks that are the same size order and they're both free, we can coalesce them into a larger block that's also contiguous. And so by managing page frames with a binary buddy allocator, we can try to coalesce and reclaim as much of that physical memory as possible to make sure that we're in a good position to help peripherals work. But even then, Linux still has some issue with the fragmentation of those physical address ranges. And so in really serious circumstances, it just makes sure to grab a chunk of physically contiguous memory at boot time so that it's available for devices to use. Okay, so I wanted to mention that. And below the binary buddy allocator, it's using a slab allocator to allocate individual objects. So you can imagine kernel code comes in, I need a file thing, I need a task struct to manage a new kernel thread or something like that. It asks the slab allocator goes and grabs an object out of a slab that's part of a cache. And if the slab allocator says, ooh, I need to allocate a new slab, then it'll turn around and ask the page frame allocator for a contiguous region of a certain size. And the binary buddy allocator will take care of that. Okay, so that's the whole picture. One of the last things that I wanted to mention about this is that hardware caches, again, raise their heads in these pictures. Because what can happen with a slab allocator is you end up with a cache, and you might end up with 5 slabs, 10 slabs, 20 slabs that all have the same size objects in the slabs, and the objects all have the same addresses relative to the start of the virtual address range. And I mentioned that hardware caches play tricks with cache line placement based on the address to make sure that cache lookups are as fast as possible, which means when you have real regularity in your address sequences, this can generate some major issues with hardware cache interactions. And so when you have these kinds of situations, you can end up with problems. They're called conflict misses. And it's an important performance issue that can occur. The upshot of a conflict miss is because of your memory access pattern, the cache looks way smaller than it really is. And so you basically incur the performance cost of accessing main memory instead of getting the benefit of using the cache. And so there's a technique that has emerged with slab allocators that's really cool, and it's called slab coloring. And so the idea is when you're adding slabs to a cache, remember these objects are a certain size and the slab is a multiple of virtual memory pages. Almost always you're going to have a little space at the end. You're going to have a little bit of memory you aren't using, you can't use. And so slab coloring basically allows you to put a little bit of that excess space at the beginning instead of at the end of the slab. And so you can assign each slab a slightly different color, and that shifts all the objects within the slab, and that makes their addresses far friendlier to the hardware caches and the interaction between the hardware caches and the kernel's access patterns. So that's what slab coloring is, if you ever come across this term. It's a really neat thing. Okay, yeah, so the cache descriptor would say, here's the min color value, here's the max color value, here's the color increment value. And a lot of times, if you understand how the hardware caches work, and the processor x86 will tell you about the hardware caches. It has a special instruction called CPU ID you can use to query what hardware caches are present and what's their layout, what's their architecture. And you can use that information to pick slab coloring configuration to make your kernel play nicer with the hardware caches. Okay, so this is what I was mentioning before. Linux started using a slab allocator in 2.2, and because of the issue of physically contiguous address ranges, and of course Linux wants to be fast, so they have DMA transfer support for as many peripherals as possible, and that means that you frequently need physically contiguous runs of page frames for the peripherals to write into. It uses binary buddy allocator for that, to keep physically contiguous regions, and then that is going to sit under the slab allocator, which the kernel can use to ask for DMA friendly or non-DMA friendly buffering for various purposes. Okay. And the Linux slab allocator, as I say here, each cache contains slabs that are all the same size. You might remember that the zone allocator can choose a number of pages for each allocation in the zone, but the slab allocator keeps it simpler and just all the slabs are the same size in a particular cache to keep it simple. Okay, what else do I say? Yeah, so they can be 3 different states, so this is nice. You'll notice full empty. We would like to try to allocate from partials rather than empties because empties can be reclaimed. And if we ever get a slab back to the empty state, then we can go ahead and reclaim it. Okay. So pretty straightforward. I don't know. I think it's conceptually straightforward. The devil's always in the details, right? But conceptually, it's very straightforward. Okay, so that's all I wanted to talk about with kernel allocators. Hopefully you enjoyed that somewhat whirlwind tour of kernel allocators. And next time we will pick up the next topic for the operating systems assignment. So see you next time.